Okay, coming back with the video once again. Today I'll be trying to simulate the Affine Cipher, Affine Cipher, whatever the pronunciation is, I don't care. The Affine Cipher is one of the monoalphabetic ciphers, and it is a combination of these two, the additive cipher and the multiplicative cipher. Basically, we will do this using keys. Okay, this is coming under the family of symmetric key ciphers. Symmetric key ciphers has one public key. You use this public key to encrypt something, and you use that to decrypt something. Without the same public key, you cannot decrypt it. So suppose if I have anything, for example, let's say computer architecture. Okay, I want to encrypt this, and I got some gibberish. Okay, I got some gibberish. Now, if I want to decrypt this gibberish back to this form, I will need this public key. Without this public key, I cannot get back my values. So before I go to public keys, I want to define what the Affine cipher actually looks like. And to be fair, I don't have it written down anywhere. Actually, I do. One second. Let me check. Files, programming, LaTeX, this thing. Alright. So yeah, this is the Affine cipher. So if I have a plain text called P, plain text, something that is mentioned with computer architecture, this is my plain text. It is normal, readable English that you can read. I want to encrypt it using some keys. Okay, so this is my plain text. These are my keys, K1, K2. So this cipher will look like my cipher text will look something like this: P times K1 times plus K2 mod 26. We take mod 26 so that the encryption stays in the alphabetic range. There are 26 alphabets in the English language. There are some constraints though. The first constraint is that the value of K1 must be taken such that the multiplicative inverse of it exists in the set Z26. What this means is Z26 is basically all the numbers from 0, 1, 2, up until 25. Alright, up until 25. So what we are going to do is we will multiply all these numbers each time with 26. Okay, 26. And after doing that, we will add 1 to it. Okay, what I'm going to do is basically I into 26 plus 1. This is what I want to do. And this is equal to some integer k. Okay, this k value will be co-prime to 26. Okay, the logic why we are doing this, I will come to that later on. Okay, but first we'll just discuss the constraints. This is my first constraint. It should have multiplicative inverse. So if I apply this algorithm to each term over here, then I will get this series. 26 into 0 plus 1 is 1. 26 into 1 plus 1 is 27. 26 into 2, that's 52, plus 1 is 53. So I'll get these numbers, it's a list. So now, I must make sure that if I choose K1, anything, then the inverse, okay, inverse of K1, I actually didn't mention it properly here, but the inverse of K1, it should exist in this set. What is the inverse of K1, how will you find it? Usually in cryptography, if you want to follow the traditional method, you use this formula, it's called the extended Euclidean algorithm. Okay, so you find the inverse, the modular inverse of a number using this algorithm. Okay, but in our case, we'll just use the brute force method. We will brute force it, and we'll see, suppose if I choose K1 is 3. Okay, suppose K1 is 3. So I have K1 is 3. I'm multiplying it with this. We don't need to worry much about K2 because K2 is the additive inverse minus. Additive inverse will always exist in this set. Always. Always. Because it is, you have to subtract it from 26, right? So you will get that without any issues. But multiplicative inverse you may not get. Suppose K1 is 3. Okay. Now I have to find which of these has a factor of 3. Okay. So if I look at 1 does not have a factor of 3. If I look at 27 is basically what? 3 times 9, right? So in this case, 9 is the multiplicative inverse of 3. So when I reconstruct my plain text from my text, I'll be multiplying here with 9. That because 9 is my multiplicative inverse of 3. So I need to check that this exists. The multiplicative inverse of K1 exists. That is my constraint. That is one of the constraints. We have other constraints. We'll discuss them as we go along in the code. Another thing I want to mention is how we are generating K1 and K2. I want to generate absolutely random numbers. Okay, because the idea is to encrypt each of these characters with a different K1 and K2 value. Right. So for that we need to generate an array, a list of K1 and K2s, a list of numbers, random numbers basically, pseudo random numbers. For K1 I'm using the LCG method, the linear congruential generator. For K2 I'm using the BS, the Blum algorithm. We'll discuss this in detail as we go. So that's pretty much everything. So we'll start with the programming. Okay, coming back to this code. These are the numbers that I choose. These are completely random, but they have some meaning. All of these are prime numbers, and all of these, obviously, if it's prime, then they will be co-prime to each other. But one thing that's more important is that A has to be co-prime to 26, not 26, mod n in this case. See, for LCG, the linear congruential generator, the relation for generating the seed each time, you have a recurrence relation. This is the recurrence relation, where x of n is my seed that I defined over here. This thing, where is it? Yeah, this thing. This is my x of n, and x of n is the next iteration. The seed for the next iteration. Mod m is just a prime number. If I choose it very high, then what's the word for that? I'll just get a better resolution for my randomness. A and m should be co-prime. A and M should be coprime. So and C can be anything between 0 to M in this case. So x of n is the current state of seed, A is the multiplier, C is the increment, and M is the modulus. Now a random number will be generated by this formula. We will scale it down by this value. The reason we are doing that is so that it stays from 0 to 25. We'll come to that later in a short time. Now I'll just quickly define. Okay, I have defined this range with minus LB plus 1. This plus 1 makes sure that both the limits are included. So if I want to put 0 to 9, I want to make sure that 0 is also included, 9 is also included. Now I'll just iterate. I need to iterate from this to that, right? What else do I need to seed? Okay, so this is the seed value. So we'll put this in a formula. So seed is equals to, let's say A mod A times my seed plus C mod M. This is what I'm going to do. The seed recurrence relation. Not of that. And random numbers are defined with this. Min plus max minus min. And that. Max minus min. So actually I've already defined this in my range size of this thing. I'm doing plus 1. I didn't mention plus 1 over here because this algorithm sort of does not take into account both the limits, and also this code is for MATLAB actually. I did this code for MATLAB, so over here you can see I've done this. So random numbers I've done this, min val minus max val minus min val. But in Python I'll just add plus 1 to include both the things. So random numbers min val lower bound plus. Okay, why I'm doing lower bound plus is that I want to shift it from the lower bound. Okay, so if assume I had lower bound to be 5, okay, and upper bound I had say 15. So I want my random numbers to be between 5 and 15, right? So this, shifting from 5, so I'll add 5 to whatever value I'll get, right? I'm scaling down between this range. That is why I'll do mod M also afterwards. So I'll do over here, what is the formula? This into seed mod thing. What's the formula? Right. I haven't actually divided by that. So let's see. Okay. Range size into seed. This thing I need to do with mod M actually. In our case, let me verify if that's actually correct or not. Hold on. Let me check. Okay. In seed I'm already doing mod M, right? So over here I'm not going to mod M. I'll just do seed mod range size. I want to basically keep my random numbers inside this range that I defined. Okay, so if it is 5 to 15, I will get numbers within 5 to 15. So like 5 I will get, 6 I will get 7. Up until 15 I will get all these values randomly in a random sequence. We will see how that's happening in a short, right? So I'll redefine back to 0 and 9. And these are my random numbers. So I'll just return this. Return random numbers. This is what I'm getting. Let's see if I'm getting this correctly. LCG n comma c n comma c. What is n? I have a string and I'm putting it from here and 21. Okay, so this n will be the length of my string. Okay, so this n is actually telling you how many random numbers you want to generate. Okay, one for each character in my string. So let us test if this works. Enter. So suppose if I enter my name, I'm getting these random numbers. So there are actually 7 letters in my name and I'm getting 7 random numbers. So I think this is working. So you got everything from 0 is also included, 9 is also included. So this is working. This means this is working. So this is the first part and that is cleared. I can delete this one, I'll add it later on, or let me just keep it actually, doesn't matter. Next thing that I want to do to simulate the Affine Cipher is K2. So for K2 I need to use the BBS algorithm. So I'll make another function BBS, and here also I'll just give the n value, how many numbers I want to generate. So BBS algorithm goes something like, actually I just won't explain everything too well. I'll just briefly tell you what to do. I need to choose 2 prime numbers, P and Q. Okay, I need to choose 2 prime numbers. So, BBS algorithm. Okay, I need to choose 2 large prime numbers, P and Q, such that if I take mod 4, then I should get the remainder as 3. So P mod 4 should be 3, Q mod 4 should be 3, anything I can take. So basically the remainder should be 3. So I can take P as 7, Q as 11 randomly. Then I need to define the number n, that is the multiplication of these two, P times Q. After that I need to choose a seed, a random seed. Condition of the seed is that my seed should be coprime to n, means the GCD of my seed and n is this number over here. It should be 1. They should be coprime. Also seed should be greater than both of these, 7 and 11. So I can choose 13 over here. Right. You can see n will be 77 here. N will be 77. 7 times 11, that's 77. And that's pretty much the condition of the seed. After that, the algorithm. Right. So the algorithm actually looks something like this. So x of I plus 1, that will be x of I plus square mod n. This is how I generate my random numbers. This is the algorithm. So I will use a for loop for this. and take the square. Yes. Okay. After this, the random numbers that I will generate. CBBS algorithm basically gives you the random numbers in a binary sequence, binary random numbers. So all I'm going to get is 0, 0, 1, 1, 0, okay, something like that. Completely random sequence, but in binary. To get binary values, I need to extract the least significant bit, the last digit of this. How I'll do that? I'll just check if it is even or odd and take the mod 2. So LSB equals to x mod 2, basically. So x is my seed. Okay, what I'm doing here? Where did it go? I haven't mentioned this anywhere in my report, but this is how I'll get my random numbers. Again, I'll just define a random number list that has the same length as n. Yeah, that's the thing. Yes. So this will also generate random numbers, right? That is pretty much everything. So all I need to do is I just need to define k1, k2. K1 will be LCG of n, and the seed that I want to give. So see this entire thing over here, this thing. Yeah. And k2 will be EVS of n. These are two values that I need. Right. I have k1 and k2 right now. Now the biggest problem that I had, the constraints. Okay. Here, k1 should have the multiplicative inverse. So we need to check if the modular inverse exists in the set of Z26. So the condition for that is GCD of k1 and 26 should be 1. Okay, if that is satisfied, then the multiplicative inverse will exist. Otherwise, it will not exist. So GCD of k1 and my mod number, which is n in this case, which is 26 in this case, that should be equal to 1. If this is happening, then I can say that the modular inverse exists. So I'll just define a GCD function. Here I will give two variables over here, and I need to find the GCD of two numbers. So how do we do that? While b, I think that should be it. This should do it in GCD. Yeah. Yeah, right. Right, so while b, so unless b reaches a value 0, till then this will run, and we take the remainder and storing it in b, and we're updating a also with b. So finally we'll get a, the greatest common divisor, basically the ladder method, but smaller because I'm lazy. That's GCD done. Now I need to check if k1 is valid. So I'll define another function. Def. These are the mod values and k values. So like I said, the GCD of k1 and mod has to be 1. If that is not 1, then for that case I will define this function while not equals to 1. So for this case we'll do something, and otherwise we'll just return k1. Okay. Actually I think there should be else solution because there is no condition, so we'll return k1 if there is nothing there. So what we actually do over here, we increment k1 until we find the perfect value. Let's increment by 1. This should work technically. This will go over here and this will keep on running infinitely. But I also want that k1 should never exceed mod n, mod means 26. Otherwise that will defeat the purpose. So if k1 is greater than or equal to mod, then I will redefine k1 as 1. I think that should do the trick. Yeah. So this is a function that returns the k1. If you had any knowledge of this algorithm, you would understand this would perfectly make sense. But for now, just look it up. Yes. Okay. Yeah, so I was saying, if you knew the Euclid's algorithm, then this would make sense. This is how it works actually. Basically, we take two values, t0 and t1. So one of the values is assigned 0, another one is assigned 1. Then you have r1 and r0. So sorry, r1, r2. So r1 is defined with the mod and r2 is defined as k1. We check for the remainders. We divide it by this value and we check for the remainders, and then we update the values. We do this till r does not reach 1. Okay, something's wrong. Yep, that's what I think. Okay, 1, 2. Right. So if t less than 0, this is just so that t does not exceed the mod value. T does not become negative. If it becomes negative, then we'll add it with the mod value. That's how we find mods. Right. So if something mod something is equal to some negative value, then you'll always prefer the positive value. So you will just add 26 with the value that you got. So for example, if I got 3 mod 4, this can be -1, okay, or this can be 3. If you get -1, then you just add 4 to this thing. -1 plus 4 is equals to 3. So this, you will prefer the 3 value more. That's just the way we do things, and that is our final value written on T. So right now I have the modular inverse of K1. In my Affine Cipher, I will use these things. Right, so I will define the Affine Cipher. So I will need a plain text, and I need K1 and I will need K2 for this. Okay, here I will store the correct K1 values. The thing is, like I mentioned before, K1 must have a multiplicative inverse in this set of Z26. Right, so I will verify if the mod inverse exists or not using this function. And if it does not exist, I'll find another K1 that has an inverse. I'll return this K1 and I'll store it in this final K1 list. And I will use that only to encrypt my thing. So I'll just define this length of plain text. What is a for loop? Iterating through each character. If character is an alphabet, then I'll check these things. Actually, I'll check two things. If character is an alphabet and if character is a lowercase. Right. Why? Because I'll get to that in a sec. And if char is alpha and these will be odd of 8. Right. Why am I doing all this? What is the meaning of all this? Basically, I want to encrypt something. Now, by how much will I shift? From what value will I shift? Okay, so if I have a random letter, say suppose A, okay, and my K1, I'm multiplying it with K1. Forget multiplication, just add it with K1. Suppose K1 is 3. Okay, so if I want to add A with 3, then after 3 letters, what is the letter I get? A, B, C, D, E, right? E. Now, ASCII value of A is 97, small a, that is 97. If I add it with 3, right now, because I'm within this range, I will get E. Okay, I will get what I want. Maybe not E, maybe D I'll get, because this will include the last letter. So, maybe this will become D, right? But what if I have Z over here? So, outside the set of Z is what, like 97 plus 20, 26, how much is that? So, it's 123, I think so, 123, if I'm not wrong. So, if that happens, 123 is not an alphabet in the ASCII value. So, how do you tackle this? I mean, basically it goes out of range, okay. So, if I want to tackle that, then I have to scale, I have to shift it from that to what I want. So, I have to minus by 25, 97 basically. My base is odd of A. This gives me the ASCII value. So, basically base is over here, it's 97. And if I subtract whatever character I have by 97, I'm subtracting each character by this base by 97, right? So, then the range that I'm getting is from 0 to 25. This is all it. Basically 26 alphabets are cleared, but from 0 to 25. Now it doesn't matter if you shift from the anything. Also, one more thing, the key values are limited to 0 and 9. So I will get values. Right, was I? Yeah. So the reason we are band limiting this to 0 to 25 is because ciphers like Affine ciphers and other ciphers, which and all that, they use indexing from 0 to 1, 0 to 25. They shift the letters indexes, not the ASCII values. Another thing is during decryption, I will need numbers that have multiplicative inverse. That is why we are doing this. The final condition here is if this is not an alphabet, in that case I'll just add it. I'll just leave it as it is. I will not do anything to it. And this is my cipher. Okay, first I'm checking if characters alpha, and then I'm going to check if it's lowercase. These will be our thing, 97. If it's uppercase, then these will be 65. That is the ASCII value of a capital A. And then, yeah. Encryption, what's the file? P times K1 plus K2. Character times K1 of I plus K2 of I. K2 is still, it's an array, so not 26. I think that should be, yeah. No mistake, this character should not be there. I should multiply with x, because this is the numeric value of p, which is the element we are trying to shift. Shift, or you can say encrypt. X is the numeric value of this character. So I am changing x by shifting it with this base, band limited with base, so that it comes in a range of 0 to 25. And that is my p in this formula. Here, this is x. So that is the thing. Yeah. These given features will be the inverses. This is the additive inverse, this one, and this is the multiplicative inverse. So I'll define it like this. So it's not inverse, K1 and mod. Define mod as 26. Right, so for I in range cybertext. We will follow the same thing. The difference of this will be cybertext. This one also. Decrypted of I. So according to this formula, I need to first subtract and then multiply with this inverse. So K inverse times subtraction. Ciphertext. Now ciphertext is basically this. So I'll have to do x minus K2 inverse. I also need to find out the inverse of K2. this is only its inverse. And then we have to do mod whatever 66. So that is our thing, and we will return this value. Yes. So yes, index Q1 and Q2. Index encrypted text K1 and K2. Now the problem is we need it to be inverse. I need to return something from here again. I need to return the final K1. So yeah, so basically first output will be this, the encrypted text. Next output will be final K1. I'm storing that over here inversely. So here I will input inverse. I think that should sort of work in my case. The encrypted text is encrypted text and print the decrypted text is decrypted text. I think it should work. Computer, here. Okay. Affine Cipher. We need to get the model. So I'll just define model here. Model equals 26. That should work. Where are we checking that? Find valid K1 GCD. Okay, now wait, K1 is okay. Let pass this thing. I'll pass a list. K1 5 index out of range. Okay, so load. I think this should work. We kept this. Okay, one sec. These typos. Okay, quotient was modulus. Okay, int and list. How is it list? What is K1? Mod inverse. Where is mod inverse? Okay. Okay. Alright, 1 second. I am getting the value from here. K1 is this. Inverse K1 is this. Right. Inverse K1 comes from here. This is an array. List. I used to code in Java, so old habits. This is a list. Mod inverse. What's happening? Mod inverse. Decrypt inverse clear. Inverse clear in decrypt. This is a reason. It's an array. Here is an array. This cannot be an array. So for each value I need to find out. Right. So I'll just delete this and we'll just put it here. This will be K1 of I. that's done. Few changes that I made was this was the string, so I had to return the string value, and after performing this operation I have to add the base value because we did a band limit operation from 97 to 0. So we need the ASCII value back, so that's why we need to add by base. Same thing over here. When we add the base, we get the ASCII value back, and then we do CHR to get back the character from the ASCII value. And in the end, this is the program.